You press a switch. A lamp wakes. Somewhere beyond the wall, a little more electrical power is being used than it was a moment ago. Your lamp did not send a request to one chosen generator. It joined millions of other changes inside one interconnected system, and that system immediately began to respond.
Across much of North America, alternating current repeats about 60 times each second. That shared frequency is not a decorative number. It is one of the clearest signs of balance between power entering the system and power leaving it. When demand rises, the physical system feels the imbalance before any operator can pick up a telephone. Rotating generators briefly surrender some of their stored motion. Their speed, and therefore system frequency, tends to fall. Controls can add power. Other equipment can change demand. Operators have already arranged reserves and procedures for larger disturbances. These reactions unfold at different speeds, from fractions of a second to minutes and hours.
So the first negotiator is physics. The next is automatic control. Then come operators, forecasts, contracts, prices, and rules. Calling this a negotiation is a metaphor, but a useful one. No single participant commands every electron, and electrical power follows the conditions of the network, rather than a route chosen like a parcel in the mail. De-energized. The grid is steel, copper, concrete, transformers, cables, and silent machines. Energized, it becomes a continuous event. Loads change, weather moves across lines and solar fields, power plants start and stop, protection systems watch for danger. People revise plans while the system keeps moving.
That does not make the grid alive. Automatic response is not thought. A relay does not understand a storm, and a generator does not intend to rescue its neighbors. But the behavior of the whole system cannot always be inferred by staring at one component. Interactions matter, and sometimes they produce outcomes that no participant selected.
This is where the Santa Fe Institute's recent question begins. A 2026 working group argued that today's power system should be studied as a complex adaptive system. Hardware joined to people, organizations, markets, software, and regulation. It is a research agenda, not a finished theory, and its value depends on what it helps us see. Consider a house with rooftop solar, a battery, an electric car, and a smart thermostat. At noon, it may export power. In the evening, it may import. Its battery can wait for a cheaper hour. Its thermostat can briefly ease demand. The old picture of a passive consumer at the edge of the grid is becoming harder to draw.
An aggregator can coordinate many small devices and present them to a market as one larger resource. In the United States, FERC Order 2222 created a route for such aggregations to participate in organized wholesale markets under federal jurisdiction. The details vary, implementation is uneven, and the order does not apply to ERCOT.
Now the wall socket is connected not only to power stations and wires, but to software decisions made in homes, cars, companies, and markets. A price signal changes when a battery charges. That changes demand. Demand changes operating conditions. Those conditions can change the next price. The grid has acquired more feedback, not necessarily more wisdom.
A real disturbance shows what coordinated response looks like. During the 2011 Virginia earthquake, several large generating units disconnected in seconds. Frequency dipped across the eastern interconnection, but other generators automatically increased output, helping contain the event before slower actions followed. No machine understood the earthquake. The designed responses worked together.
Complexity has a darker face. During the February 2021 cold emergency in Texas and the south-central United States, extreme weather struck electricity production, natural gas supply, equipment, operations, and preparation at the same time. The official investigation describes interdependent failures, not one magical broken part.
This matters because a system can adapt in ordinary conditions and still fail under stresses its institutions and equipment were not prepared to absorb. More connections can share support. They can also transmit trouble. More automation can react faster. It can also create new cyber and coordination risks. Adaptation is a capability, not a guarantee of resilience.
Can the grid learn? Individual algorithms can learn patterns. Operators and organizations learn from events. Regulations change. Consumers respond to prices and outages. Technologies that work can spread. Those that fail can disappear. Across years, the combined system remembers through code, standards, equipment, institutions, and human experience.
Researchers at the National Renewable Energy Laboratory are testing distributed and hierarchical controls that coordinate very large populations of devices. One experiment optimized more than 1 million simulated resources alongside smaller real systems. That is important evidence of scale. It is not evidence that a national grid already runs itself.
There is another loop. Electricity powers mines, mills, factories, data centers, and transport. Industry produces transformers, cables, controls, and machines that repair or expand the grid. The expanded grid then supplies more industry. From far enough away, the system seems to help produce parts of itself. But the phrase hides its most important actors. The grid does not mine copper, decide who bears a cost, finance a factory, train a line worker, or choose where a transmission line should go. People, firms, governments, communities, and ecosystems close the loop. What appears self-producing is really a technological ecosystem embedded in society.
A complex systems lens is useful when it reveals feedback, delayed consequences, coupled risks, and behavior that emerges from many decisions. It becomes dangerous when words like evolution or self-organization make accountable choices sound inevitable. Power flow, protection, stability, maintenance, planning, and governance do not disappear inside the metaphor.
The grid is not an organism. It is not conscious, and it does not reproduce. Yet it is no longer convincing to describe the live system as inert hardware alone. It is a negotiated arrangement of physics, machines, people, software, markets, weather, and rules, continuously holding a balance none of them can hold alone. The next time a room brightens at the touch of a switch, the hidden event is larger than the lamp. A continent-sized system has absorbed one more change, not because it is alive, but because generations of engineering and institutions have taught a machine made of many actors how to keep negotiating every second.